Hi, welcome back. Let's change gears and talk about the wave nature of light. So far, we have studied interesting aspects of light, described as rays propagating in straight lines and bending their trajectory when entering a different medium. There are lots of interesting aspects of light behavior that can only be understood if we consider light as a wave. To describe a wave, let's first consider an arbitrary shape that is moving. For example, a pulse that maintains its shape and moves to the right. We can mathematically describe this shape from the reference frame of the laboratory x and y, or from the reference frame addressed on the moving shape, x prime and y prime. The curve can then be written as y prime as a function of x prime. If this is a pulse propagating on a rope, y prime is the height of the pulse and f of x prime is its description as a function of the horizontal coordinate. If this is a pulse of sound, y can be the increasing pressure of air as a function of the position. The y, the height in a rope, will not depend on the reference frame, if it is on the laboratory frame or if it is on the pulse frame. Because we know how to change coordinates from one reference frame to another, we can write this as y equals to y prime equals to f of x prime equal to f of x minus vt, which we learned from Galileo. So the intensity of the height of the pulse depends on the position x, on time t, and on the velocity of the pulse v. The argument x minus vt indicates that the shape does not change, but it is translated along the x-axis by the amount vt. This pulse can have a weird shape and still satisfy this description. Now, I want to find an equation that describes the evolution of the wave, its evolution in time and in space. I want to find an equation that tells me how y is going to change as I let time roll and also as I move on space. If I pick one point on the pulse and I neglect the rest of the wave, how is that point going to evolve in time? If I pick one instant in time, how is the wave distributed on space? To answer that, to know how y is changing in time and in space, I need to calculate the derivative of y as a function of time and position. If you remember from your classical mechanics course, the equation of motion of a particle is described by the second derivative of the position with respect to time, which is the acceleration. But that is related to the force, which could be related to the derivative of the potential with respect to the position. So I have y equals to f of x prime, and I have that the relation between x prime equals to x plus or minus vt. Here the plus sign indicates that the pulse is moving to the left, and the minus sign indicates that the pulse is moving to the right. So I calculate the partial derivative of y with respect to x, which is the partial of f with respect to x prime times the partial of x prime with respect to x. This latter is 1, so the partial of f with respect to x is equal to the partial of f with respect to x prime. I'm going to derive this again using, again, the chain rule of derivatives. Now I'm going to derive y with respect to time t. Partial of y with respect to t is equal to partial of f with respect to x prime times the partial of x prime with respect to t. I'm deriving again with respect to time using, again, the change rule of derivatives. Now I compare these two results and it happens that they only differ in a multiplicative factor. so I can join them into this differential equation on partial derivatives. This is the cold wave equation, and any wave described by y equals to f of x plus or minus vt will satisfy it. If a function y of x and t satisfies it, then it describes a traveling wave. This is satisfied by some waves, by waves on a rope, by electromagnetic radiation, by gravitational waves, and so on. Of course, there is a case of particular interest, which is a periodic harmonic wave described by a sine or a cosine function, such as. But we'll talk about this in the next lesson. Meanwhile, may science be with you.